Hi, in this video I'm going to answer the most mysterious question of them all. Who is this guy who keeps talking to you about physics? That one. Alright. My name is Philip, I'm your instructor, as you hopefully have figured out by now. And I've been at Western now for 2 years. I'm also currently teaching at Whatcom Community College and at Bellingham Technical College. And in the past I've also taught at Skagit, so I've sort of taught at every single college in the area. I did my undergrad in physics and philosophy in Oxford, at Oriel College in the UK. So I actually got a sort of double major, and part of my degree is in philosophy. Then I did a master's in theoretical physics at Imperial College in London, and then I did my PhD in Clemson, South Carolina. How did I end up there? Well, long story. Not going to tell you that about that now. I did my PhD there. My sort of area of interest, my research area, is broadly speaking quantum gravity and quantum foundations. Now, if you want to understand what that is, let me try to explain it. So we understand gravity pretty well, right? We understand how to calculate the motion of planets, how galaxies form, and so on and so forth. Yes, there are some open questions there, don't get me wrong, but on the whole, we understand gravity pretty well. We've got a good theory of gravity called general relativity that is fairly well corroborated, meaning that we've got lots of evidence, experimental evidence, observations, to think that our theory is true, or at least is an extremely good approximation of what reality, what nature actually looks like. So this is gravity, right? Gravity works for, stuff that has a lot of mass, like planets, galaxies, and stars, and all that stuff. We also have a really good understanding, by we I mean, we as physicists, we as the scientific community, we as, mankind, if you like. And we have a really good understanding of how small stuff works. And the theory sort of framework that describes how small stuff works is called quantum theory. If you go to small stuff that's also moving very fast or has very high energies, we talk about quantum field theory. And again, we've got a lot of experimental evidence to suggest that our theory is really good, that we have a pretty good grasp on how nature works. So one sort of drive of physics throughout the ages has always been to sort of find an overarching, unified theory of different things. So one example is electricity and magnetism. Totally different things until you study them more and you figure out, hey, they're actually just aspects of kind of the same thing. So this is one example, right? Or the realization that the force that keeps planets in their orbits is the same force that makes stuff fall down to the ground on Earth. Right? It's not obvious, but both of them are gravity, and it's one law ultimately that describes them all. So we've got a really good theory of gravity, we've got a really good theory of quantum mechanics, quantum field theory. And now if you try to put them together, if you sort of try to what's called quantizing gravity, so you apply what we know about quantum theory, we apply it to gravity. And you might think, why should we do that? Well, one thing is just having a general theory of everything, if you like. But the other part is that we might want to think about, what happened at the very beginning of the universe, the first fraction of a second. At that point, we'd have very high energies, but also a lot of mass in a tiny space. So, kind of both theories should apply there. So you try to put those together, quantum field theory and general relativity, and you end up with a disaster. Like, the theory doesn't make any sense. You can sort of do it, like the math, you can write it down, but what it predicts is that nothing ever happens. So the universe is just frozen in time. Like, the laws of physics combined, right, tell us the universe is frozen in time. Now you look at the universe and it's not frozen in time. Stuff is changing, stuff is happening. So So that means somehow this naive way of combining the two just doesn't work out. And so that's why we have to find a true theory that, when it comes down to it, acts like general relativity when we talk about planets, and acts like quantum field theory when we talk about, protons and neutrons, tiny, atoms and smaller particles. But we don't know what this sort of original theory that would include them both is, because the naive way of combining them just doesn't work. And so there are lots of, ideas out there. One of them is string theory that you might have come across, but it's just one, theory it's very hypothetical. It's speculation, right? There's a lot of math behind it, but there's no experimental evidence. So it's not a well corroborated theory. It's not, there's not been any experimental test to suggest that should be right. There's what's called loop quantum gravity. It's another example. Also trying to make mathematical sense, coming up with something that looks like general relativity, it looks like quantum field theory, and is consistent. And again, there's no way to say, we have got no experiment that says that is the right way to go. So those are just the two main approaches. There are a bunch of others. My personal interest is essentially the question is, are the foundations of quantum theory right in the first place? So saying, okay, general relativity seems good, although, as I said, there are open questions there too, but really, is the way we're doing quantum mechanics right in the first place? Yes, a lot of evidence, but that could be explained with a different framework than the standard quantum framework. Because the standard quantum framework doesn't make sense in the first place. It has conceptual problems. Right? It's kind of a machine that gives out the right numbers, makes the right experimental predictions, and there's no doubt about that, but the conceptual framework that underlies it just doesn't make sense. It's essentially trying to work towards a theory of quantum gravity where we rewrite the rules of quantum mechanics in the first place in a way that they make sense and that they also are consistent with combining them with gravity. That is kind of broadly speaking, the area I'm working on. That's about me now. Like any academic, I guess, I tell you all about my work and my CV essentially, but not who I am beyond that, so let me at least try. I live in Bellingham. I've got a wife and 2 kids. My wife actually works in the English department, and if you want to declare your English major, you have to go through her at one point in your academic career. I've got 2 sons. They're 5 and almost 5, and 2, and they're the ones that stop me from getting any work done. Beyond that, outside of work, what do I do? Do I do anything? I guess I play the piano. I practice Wing Chun Kung Fu twice a week, though right now, with the Corona crisis going on, I sort of try to do it at home, a bit difficult. I cook, especially curries. I cook curries all the time if it were just up to me. So yeah, that's kind of my life. So now you know who I am. Now you know who this mysterious face is that keeps talking to you about physics. And now you can go back to your studies. Over and out.